Hello, AP Physics 1. Here are the solutions from part 1 of the Chapter 7 textbook homework that you requested that were not already in the homework solutions videos. So we have questions 7, 8, and 11. So for question 7, we have, according to equation 7-1, the longer the impact time of an impulse, the smaller the force can be for the same momentum change, and hence the smaller deformation of the object on which the force acts. On this basis, explain the value of airbags, which are intended to inflate during an automobile collision and reduce the possibility of fracture or death. So what they're referring to is that you can have two ways to change the momentum, or two ways that you can have an impulse be applied to an object. So you can have a large force and a small time, but that would be the same quantitatively as if you had a small force and a large time. So it depends on what you're looking to do. In the case of a car accident, you want to go for the smaller force to slow down the passenger or the driver using the airbag. So in this picture, you can see that on the left, with no airbag, the driver's head hits the steering wheel, and there's a very short time in which the head is slowed down. Whereas in the right picture, that's green is good, you have a lot more time to slow down or apply that force to passengers or the driver's head. So that's all 7 was really looking at. For 9, we have a boy that stands on the back of a rowboat and dives into the water. What happens to the boat as it leaves? So since the boat is in the water, there's very little resistance. So just from experience, you can kind of see that the boat would go back the opposite way. Same thing if you were standing on a skateboard or something like that. So just to kind of talk that out in more detail. So if you had the boat and you have the boy standing on one side, initially there's no momentum, right? It's going to be that kind of explosive or reverse inelastic collision type scenario where you have the momentum of the boy and the boat equal to the momentum of the boy and the boat afterwards. So since in the beginning nothing is moving, just some basic math, you're going to have one object go to the left and one object go to the right. So one's going to be positive and one's going to be negative, so resulting in that direction. So since most likely the boy is less massive than the boat, it's going to have probably a large velocity, where the boat is probably very massive relative to the boy, and it's going to have a small velocity. So if you're in something like a rowboat or canoe, the boat will move significantly, but the larger the boat you get, going up to like a fishing boat to maybe a yacht or a cruise ship, the boat is almost not noticeably moving. Or another way to look at it is that the boy is applying an impulse to the boat through friction, jumping off, and they each have that same impulse. They have the same change in momentum. It's just the more massive object is not going to have as great of a velocity. And then 11, the speed of a tennis ball on the return of a serve can be just as fast as the serve, even though the racket isn't swung very fast. How can this be? So first off, with the racket still and the ball moving, it says can be just as fast. So if we're assuming all energy is conserved, it's a perfectly elastic collision. The tennis ball would bounce back at the same speed. But we know that's not going to happen, just as if you just drop the tennis ball straight down, it doesn't bounce up to the same height just because of loss due to sound and thermal energy, and also air resistance. But if the racket, let's see, that's all we're talking about in 11. So let's jump over to the misconceptual questions. So we're doing 1 and 4. So in one, we have a truck going 15 kilometers per hour in a head-on collision with a small car going 30. Which statement best describes the situation? So part A, let's see if we can eliminate some of these. Choice A, the truck has a greater change in momentum because of the greater mass. So again, that's what we were kind of talking about, where you could have a massive truck going a small velocity being the same momentum or change in momentum, since they're both going to be coming at rest, most likely. Or the impulse is the same on each one, can be the same momentum as, or change in momentum as the small car, because the car has, greater velocity, or actually double in this case. So one object cannot have a greater change in momentum because impulse is equal to change in momentum. So it's the same force. According to Newton's third law, the truck on the car on the truck is the same force, and they have the same contact time. So same force to time, same change in momentum. Part B, or choice B, the car has a greater change in momentum because it's greater speed. We just kind of showed that cannot be possible. C, neither the car nor the truck changes its momentum in the collision because momentum is conserved. That's true. The total momentum of the system is the same, but the momentum is transferred from one object to the other. Choice D, which we could see that that's a correct answer. They both have the same change in magnitude of momentum because momentum is conserved. And that is also true. And the reason why it says magnitude, it's because the objects might be going in the opposite direction, so we don't want to have positive and negative saying, it's different directions, so it's a different change. Number 4, an astronaut is a short distance away from her space station without a tether rope. She has a large wrench. What should she do to the wrench to move towards the space station? So choice A, throw it directly away from the space station. That way, if she places a impulse, force times the time, on the wrench is going to go in one direction, and she's going to go in the opposite direction. Because again, it's kind of like that boy and boat problem earlier. Since nothing is moving in the beginning, the momentum's 0. That means the velocities have to be in opposite directions, or the momentums need to be in opposite directions. If she threw it towards the space station in choice B, she would go away from the space station. It's not what she's looking to do. C, if she threw it towards the station without letting go, all that momentum, all that motion is internal in her system between her and the wrench, so she's not going to move, nor will the wrench. Throw it parallel to the direction of the station's orbit. She would potentially orbit with the space station, but never actually get back to the space station. And same thing with the opposite direction. She would now maybe be in that same orbit, but move in the opposite direction.